Watching you deal with the pee on yourself.
No.
No, we're not going to get gross and come on. It was just water.
I was kidding.
No, you weren't. This
I think you
looks
was.
clean now. All right. All right. So today we're going to talk about compound events. All right. Probability. There's on the back side of your wet. No. Okay. On the back side of your note sheet, there's all those formulas for probabilities, right? Okay. So we are going to cover. There's two of them. There's compound events. There's mutually exclusive events, and there's inclusive events. All right, this works really well. You got to turn it on. So we want to find the probability of mutually exclusive events and the probability of inclusive events. You probably don't know what those terms mean yet, but we'll talk about them here today. All right, a compound event is an event made up of two or more simple events. Okay?
You have a problem.
Yes, I have lots of them there. It's all, they're over here. All right.
What about Josie?
She's been taken care of. Mutually exclusive events are events that cannot occur in the same trial and experiment. Now think about it this way. Let's just think of mutually exclusive sets of people. Okay? Would the members of the boys basketball team and the members of the girls basketball team be two mutually exclusive sets? Is there somebody that belongs to both of those groups?
No.
No. Okay, no. Okay, so mutually exclusive events or sets are like, they can be drawn like this, and this is called a Venn diagram, B-E-N-N. There's no overlap, okay? If there was somebody that could be a member of both of those teams, this is what that diagram would look like. Okay, it would look like this. There'd be overlap. Those would be people that would be on both sets, but we don't have that here, okay? Now, if we're looking for the probability of mutually exclusive events, this doesn't work very well. All right, we have a little formula. Well, this is what is on the back side of your note sheet. This is the probability formula we're going to look at here. I'm trying to get the circle there. Now, this is basically reading the probability of A or B, okay, equals the probability of A times, or plus, excuse me, the probability of B, and that works if the events are mutually exclusive. Okay. This notation right here basically represents the word or. It's called the union of two events, or union of two sets. Okay. So it says when a number Q is rolled, the probability it's less than 2 is the probability we get a 1 or a 2. Now, you can't roll a 1 and a 2 at the same time, right?
No.
On a number cube, you can't. So they are mutually exclusive. So basically, we have to find the probability of rolling a 1 plus the probability of rolling a 2. And that's 1/6 plus 1/6, which is 2/6, which is 1/3. Okay. Mutually exclusive events cannot occur at the same time. Okay. For example, if somebody would have sat at their own desk, they wouldn't have got a wet bottom. If she would have sat at the correct desk, nothing of this would have happened, right? Exactly. That helps you understand it better, doesn't it?
Maybe you should explain it to people.
No, I don't want to. So the union symbol there, that U means or. Okay, that means or. All right. So that's one of those formulas on the back side of your note sheet. There's a bunch of formulas there, correct?
Sure.
Okay, I'm looking like right here. We're covering these bottom two here today. Does anybody not have one of these? They're available on Canvas also. What's that? That's where you get yours? Okay. Well, it's because you probably weren't here. All right. Or you were gone. All right. Now, example 1A, finding probabilities of mutually exclusive events. A group of students is donating blood. We had a blood drive on Monday. A student has a 9/20th probability of having type O blood and a 2/5 probability of having type A blood. Explain why the events type O and type A are mutually exclusive. You have one blood type, right? Person's not gonna have more than one blood type. Exactly. You have 7. All right. Person can only have one blood type. So if we wanted to find the probability that someone has type O or type A blood, since it's mutually exclusive, we can use this formula. There's no intersection. There's no people, nobody would have type O and type A at the same time. So we would just take 9/20 plus 2/5, and that ends up being 17/20. Now, what are the other options when you have blood types?
O positive.
We're not talking about, this is O, we're not worried about positive or negative, okay? You can have B, and isn't there an AB? Isn't there you guys took science one time, didn't you? Isn't there an AB type blood?
Yeah, what is defining blood type?
I'm not defining that because I'm not a science teacher.
Well,
Are
you're
we
all
talking?
lying. Yeah,
What's
you,
that?
you know.
I'm talking some more.
No, that's
I
fine.
thought you just said.
Josie, you
that-
can ask him later, okay?
You gonna give me detention for it?
No, you can talk to him later, I said. That's what I said. Yeah.
I don't see him.
Oh, you won't see him later? Okay.
I do.
All right,
No.
so the other
You have to
types,
Bring that up.
the other types of blood are B and I think AB. You guys took biology and didn't you guys talk about that in biology?
Yeah, but what?
Look it up.
Is it A, B, and
A,
B?
B, A, B, and O.
A, B, A,
And
B,
O.
and O.
Oh.
Yep, there you go. So basically, there's, 17/20 doesn't encompass all the blood types. That would, there's other options there. Okay, that's the point I'm trying to make. Now, inclusive events are events that have one or more outcomes in common. For example, if we said members of the volleyball team and members of the girls basketball team, are there some people that are members of both teams? Yes. So those would be inclusive sets of people. Okay. For example, when you roll a number cube, the outcomes of rolling an even number and rolling a prime number are not mutually exclusive, because 2 is a prime number that is also even. Okay, so notice the difference in our Venn diagram here. There's overlap. That would be like people that are volleyball players and girls basketball players, right? It'd be people that are both. The key thing here when we're talking about inclusive events is you never want to count something more than once. Okay, so if we had 40 girls on the volleyball team and 16 on the basketball team, we couldn't just say that there's 56 people that played volleyball or basketball, because there's some people that did both. So we'd be counting those people more than once. We don't want to do that in probability. You don't want to count things more than once. So if we have overlap like this for inclusive events, we'll have a probability formula that looks, I'm trying to make this larger here, like this. Okay. Probability of A union B, you could replace that with the word or if you want to, equals the probability of A times the probability of B minus the probability of A intersect B, right? This notation, and I have it on the board here, that really means the word and, right? So we'd be talking, if we're going back to the volleyball and basketball example, those would be the people that are on both teams, okay? So the example here, when you roll a number cube, the probability of even or prime would be the probability of even plus the probability of prime, subtracting the probability that it's both even and prime. Because the number in question here, 2, we counted 2 as an even number, we counted 2 as a prime number, so we can't count it twice. So this is taking out the fact that we kind of counted it twice. Does that make sense? What's the only number that's not even or prime when we roll a number cube? Even and no, what's an even and prime? Wouldn't it be? Is it 1? 1 is one isn't prime, right? You're right.
Yeah.
You're correct. 1 is neither prime nor composite, right? It doesn't fall into one of those categories. That is correct. All right. So those two formulas, know when to use them. One of them is used when we have overlap. One of them is used when we do not have overlap. All right. Recall that intersect symbol means and, right? And I have that up here on the board here also. Okay. So make sure you know the difference between or and. Okay. Or means one or the other you have to do one or the other. If I said to Avery at home, take out the garbage or do your homework, what does she have to do to make me happy? One of them, right? It's an option, isn't it? She could do both. Now, what if I said, take out the garbage and do your homework? What does she have to do to make me happy? Both. See the difference between or and? Okay. She probably wouldn't do either. Yeah, that's right. Lazy bum. All right. So here's an example of compound events. Find the probability of a number cube rolling an even number or a 4. Those are inclusive, right? Why are those inclusive? Four is an even number, exactly. Okay, so we have to find the probability using our second little formula we had there. Probability to get a 4 is 1/6. Probability to get an even number is 3/6. And there is one of the 6 numbers that is 4 and even at the same time. So that's going to work out to be 1/2. Okay. This is for compound events that are, that are inclusive. Okay. Card is drawn from a deck of 52. Find the probability of each drawing a king or a heart. Why are these inclusive? Not everybody at once. Why are these two events inclusive? King or heart? I can't hear you. There is a king of hearts, right?
Yeah.
There is a king of hearts. So there is overlap, so we'd have to use this formula. There are 4 kings in the deck. There are 13 out of 52, or 1/4 of the cards are hearts. Subtracting that 1 king of hearts, that would give us a probability of 16 out of 52, which is 4/13. Okay. All right, one more. Card is drawn from a deck of 52. Find the probability of each drawing a red card or a face card. Are these inclusive or mutually exclusive? Is there overlap in the hearts and the face cards? There are, right? Because there are red face cards, correct? Yeah, so we're going to have to use our probability formula for inclusive events. Probability of red or a face card. Somebody had a red face earlier. That's good, I'm sorry. I'm not actually, but red or face card is probability it's red, which is 26 out of 52. Probability it's a face card, there are what, 12 out of 52? And the probability that it's both is 6 out of 52. There are 6 face cards that are red, right? 3 hearts and 3 diamonds. So that's how we can find that probability of inclusive events. Questions? Have you seen these formulas before? I think you have. Okay, so you should be familiar with them. We're still going to review them and go over some more examples. All right. Now, sometimes in a question, for example, a question like this, it might be difficult to come up with the answer to this question. It says, what is the probability that a student was a senior or read the paper? When we're just given a bunch of numbers, sometimes that can be difficult, okay? Sometimes that can be difficult. So in this example here, I think I want to create what's called a Venn diagram, all right? And that's those circles that either don't intersect or do intersect. So let's read through this. Of 1,560 students surveyed, 840 were seniors, and 630 read the daily paper. So if we're trying to find the probability that a student was a senior or read the daily paper, so I'm going to say probability of a senior or read the paper, that would be the probability they're senior, plus the probability that they read the paper, minus the probability that they're, I don't know, you get myself in a room. This would be the probability that they do both, right? They're a senior that reads the paper. Okay. Now, do we know how many seniors there are? 840 out of the 1560. Do we know how many people read the paper at that school?
Yeah.
630. So we know this. The trouble here would be finding the overlap or finding out where, how many people, how many seniors read the paper. That's what we really need to look for. So I think the best way to do that would be with a Venn diagram. So here's my Venn diagram. This is seniors. And this is going to be those that read the paper. Okay. Now, this piece of information is important. Only 215 of the paper readers were juniors. Well, that means they can't be encompassed in the green circle, right? Because in the green circle, we're considering seniors. So 215 juniors read the paper. Now, knowing that is going to unlock the key to figuring out what's in the overlap and then how many seniors are there that don't read the paper. Okay. How many people should be encompassed in this circle right here? Those are the people that read the paper. 630. So how many are going to fit in here? How many seniors read the paper? If we put 630 in here, we'd have 845 people that read the paper, right? Right? Does that make sense? So you want to revise your answer? 415. How'd you come up with that? Yeah, so now we have a total of 630 in here, correct? So we kind of found that number we wanted. All right, we found that number we wanted right here, didn't we? Now, that would also mean that there are 425 seniors who do not read the paper. How did I come up with that? Well, how many? 840 minus 415 would give us 425. Okay, so knowing that one number, that 215 of the paper readers were juniors, really unlocked things for us. All right? Now, could you do that without a diagram like that? Yes. I think a diagram helps. I think that diagram helps. Okay. So I'm going to scoot ahead here and show you what they did. So remember that diagram we came up with. There's the same diagram, and we said in the green region we had 415, correct? And in the blue region we had what, 425? So our probability would be, the probability they're senior, that's 840 out of 1560. Reading the paper was 630 over 1560. And we figured that the overlap, there were 415 seniors that read the paper, right? This is that overlap right here. And we used our diagram to come up with that. So that would tell us our probability is 1,055 out of 1560, or roughly 68%. 68%. All right. Could we come up with 415 without the diagram? Yes. But I think the diagram is maybe a easier way to understand it. But that's my take. Right? Like I said, there's ways to do it without that, but the diagram I think would help. Questions? All right. Now, remember earlier in chapter 7, we talked about complements, complementary events. If I said the probability it's going to snow on Monday is 40%, what's the complement? Probability it's not going to snow would be 60%. Okay. All right. So the probability of an event is P. The probability that it won't happen is 1 minus P. Now, a lot of times when working with compound events, we're going to see the words or the terms at most or at least. Do you remember that on that worksheet that I gave you that really was a kind of before its time? Did you see some of that at most or at least? Okay, so this is part of what I was saying we were headed towards later. But a lot of times when you say at most or at least, rather than finding a bunch of individual values and adding them up, we can use complements. All right, and we're going to look at an example of that right here. All right, so here we go. Each of 6 students randomly chooses a butterfly from a list of 8 types. What is the probability that at least 2 students choose the same butterfly? Well, we could find that would really encompass 2 students choosing the same butterfly, 3 students choosing the same butterfly, right? At least 2 would be 2 do, 3, 4, 5, and all 6, right? So rather than finding all of those probabilities and add them up, we're going to use the complement. The probability of at least 2 students choosing the same is 1 minus the probability they all choose different. Because if they all choose different, the rest of the probability would be that they all choose the same. Okay. Now, a couple ways we can come up with this. right? Here's one way to come up with that number, and then there's an easier way. And if we can pick up on the easier way, that's the best way to go about it. So I'm going to try to find the probability that they all choose different. Now, would you agree the first person could pick any of the 8 butterflies out of any of the 8 butterflies? They can pick whatever they want, right? Now, the next person, they have a choice of 8, but how many can they pick if they're all going to choose different? 7. The next person still has 8 to choose from, but how many can they pick? They can only pick 6 of them because they can't pick the same as the previous 2. Are you following along here? Now, if we continue that on for 6 people, we end up with this. All right? First person, second person, third person, fourth person, fifth person, sixth person, all in line there. Okay? Now, if we can remember some things of earlier in chapter 7, we can make this much easier. First of all, the bottom is that just 8 to the 6th? It is, isn't it? Now, here's where we have to rely on something we learned earlier. What's that? Not quite. We're missing the 2 and the 1. Okay, so it's not 8 factorial, but it's close. It looks like it's 8 factorial over 2 factorial. Well, wouldn't that be the permutation of 8 things and we select 6? Because remember that formula? Wouldn't that be 8 factorial all over 8 minus 6 factorial? Would that lead to that? It would, wouldn't it? So if we can use this type of thinking, we don't have to really kind of follow what's in red. Does that make sense? If you can remember that if I deal with at least 2, I can use permutations. If I had more butterflies and more students, could I adjust the numbers accordingly? Yes. All right, so here's what they have. Basically, the number of ways 6 students can choose butterflies, that's the permutation of 8 butterflies and 6 people are choosing. Total number of ways 6 students can choose from a group of 8 butterflies. That's what we ended up with, right? And this is kind of how I led you to that too, didn't I? That's the same thing we had up there earlier. So it's not very likely that they'll all choose different. There's only about a 7.69% chance that they all choose different. Okay. So to find our probability, we're going to have to take 1 minus that 7.69%, which means there's roughly a 92.3% chance at least 2 students choose the same butterfly. Okay. Questions on that? Okay. This works really well when you're talking about at least 2, or at least 2 would be the best application here. Okay. Questions? All right. Here's a few things to work on for Monday. Monday we will review. You thought we were reviewing today. We're going to review on Monday. Monday we'll do a little review. Quizzes on sections 4 and 5 and that's on Tuesday. And we'll go from there. And I think I need to lock my door when I leave for lunch from now on.
You better.
Somebody keeps putting water on the chair.
Actually, somebody had an accident. And usually I clean up after them, but
They didn't want to.